Hello everyone, welcome to our complex numbers full course, and this course is sponsored by GAD Academy, and Academy seeks to have a full algebra course, and we are beginning today, and today we are going to tackle complex numbers. So by the end of this tutorial, we will cover everything under complex numbers. So to begin with, we start from the introduction of complex numbers. So when we begin complex numbers, one may ask, why do we do complex numbers, or why complex numbers? So there are two categories of number system. We have the real number system and we have the complex number system. So the real number system is what we use every day, and the complex number system is what we are going to do in this course. So generally, when you enter the square root of, let's say, -2 into the calculator, we end up getting error, right? So if we were to limit ourselves to square root of positive numbers, then a lot of computations wouldn't be done, because in real life, we wouldn't be only using square root of positive numbers. For that reason, scientists took to themselves to find how we can also use complex numbers in computations. So that is what we started with, the square root of a negative number I, negative number 1, to give us I, right? So now, generally, a complex number is represented as Z and is equal to A plus IB. A is a real part of the complex number. So let's make it real part. So the A is real part. The B is what we call the imaginary part. Then I is what we call the complex operator. So generally, as I'm saying, complex numbers are represented as Z equals A plus IB, real parts, complex operator, then the imaginary. So we can have an example as Z is equal to 2 plus I3, or 2 plus 3I. Any way is correct, right? So with this, we can find the square root of, let's say, -5. And this is simply equal to square root of -1 times square root of 5 from sets. This simply gives us I, because complex number system has accepted the square root of -1 generally as the complex operator I. So I simply replace this with I, multiplying root of 5. So this is equal to root of 5I. So therefore, we are having the square root of -5 to be equal to root of 5I. Now we can say the square root of -6 is also going to give us root of 6I, and it follows. So in a complex number system, the square root of negative numbers are compensated for by the complex operator I. So let's see I and the powers of I. I is equal to square root of -1, right? If I square both sides, I'm going to get I squared to be equal to -1. What if I have I cube? I cube is simply equal to I squared multiplying I, right? And from the complex operators symbol here, I is always equal to the square root of -1, and I squared is always equal to -1. So we use this as a fundamental to express any power of I for simpler expression. So I cube, I'll break it down to I squared times I, then this will be equal to I know I squared is equal to negative 1. Multiplying I, and this is equal to negative I, right? Then let's say I have I to the power 4. I to the power 4 is simply equal to I squared multiplying I squared. And you know I squared is simply equal to negative 1. I squared this one is also equal to negative 1. So negative 1 by negative 1 will give us positive 1. So therefore I to the power 4 is equal to 1. We can do that for all powers of I to the power n, right? So at this point, let me give you some simple problem here and see how we can find the highest powers of I. So this is the question. Simplify the expressions below. So simplify the expressions below. The A is what we have I to the power 25. B is 1 over I all to the power let's say 120. Then C is I to the power 201. How do we solve this? So these are typical problems you can find in the examination. So to solve this, I told you we use the basic powers. I squared is equal to negative 1. I cube is equal to negative what? I, from what we did here. So I cube was negative I. I to the power 4 was 1. So I to the power 4 is 1. So what you're going to do is, we will express this power here in terms of the basic powers. Now, I will take something like I squared. So I squared, you write your I squared. Then you ask yourself, what number times 2 will give us 25? And you know it's 12. The highest number we get is 12. So 2 times 12 is 24. There will be a remainder of 1. So meaning you get one I standing out here. So at this point, you have I squared to the power 12 multiplying I. And we all know that I squared is equal to negative 1 to the power 12 multiplying what? I, right? Negative 1 to the power 12. If you have negative 1 to the power an even number, we will get what? 1 multiplying I. Is that not it? So I to the power 25 is simply equal to I, right? Now let's see B. 1 out of I all to the power 120. This can be solved easily by removing the bracket. So I have 1 to the power 120 over I to the power 120. 1 to the power 120 is 1. I to the power 120. Now, how do we go about this? We can take a bigger power of I so that it will make things simpler. So I have I to the power, let's say 4. Then you ask yourself, 4 times what number will give us 120? Or what's the maximum number 4 can multiply to give us a number close to 120? And that is obviously 30, right? So 4 times 30 is indeed 120. Therefore, we can say 1 out of, then I to the power 4, we know I to the power 4 is equal to 1, right? So 1 to the power 30 down here. And you have 1 out of 1 to the power 30 is simply 1. Then the answer is 1. So that is for the B. Now let's see the last part, C. The C, which is I to the power 201, is equal to I. Let's take the same 4 to the power 4. Then you ask yourself, 4 times what number is going to give us 201? Or approach 201? We can say 50, right? Because 4 times 50 is 200. There will be a remainder of what? 1, which is I. At this point, I know I to the power 4 to be 1. I'll get 1 to the power 50 multiplying I. 1 to the power 50 is also equal to 1 multiplying I. Hence, I'll get I. So I to the power 201 has been simplified to give us I using the basic powers of what? Of I. And this is all about the introduction to complex numbers. At this point, let's delve into the basic arithmetic. The basic arithmetic of complex numbers. For the basic arithmetic of complex numbers, we are going to consider addition, we consider subtraction, then multiplication. Let's reserve the division after we have done conjugate of complex numbers. So I'll reserve that. And at this point, let's see addition. So let's say we have Z1 to be equal to A1 plus B1 I. Z2 to be equal to A2 plus B2 I. So if you want to find Z1 plus Z2 is simply equal to, we will add the row part together. So the row parts will be added separately. Then the imaginary parts will also be added separately. So I'll have real parts in one bracket plus I open bracket, the complex parts or the imaginary part, which is B1 plus B2. But let me make it imaginary here. So row part plus I, then imaginary part. So at this point, I'll have my row part, the total row part to be what? A1 plus A2 plus I open bracket, the imaginary part, I'll have B1 plus B2. And this gives us our sum of complex numbers. Let's take an example here. But before we take an example, let me show you how to express the subtraction. So our Z1 minus Z2 in this sense is simply equal to the opposite of what we have here. I'll have A1 minus A2 plus I open brackets B1 minus B2. And this is for subtraction of complex numbers. You only need to subtract the row parts into one bracket plus I open brackets. We subtract the imaginary parts separately. Let's take examples. Assuming I have Z1 to be equal to 2 plus 3i. I have Z2 to be equal to 4 minus I. Find Z1 plus Z2. Then find Z1 minus Z2. So this is the A part and this is the B part. Considering Z1 plus Z2, this is simply equal to, we take our Z1 which is 2 plus 3i in one bracket plus the Z2 4 minus I. As the rule said, we add the row parts together, right? So I'll add the row parts together separately. So 2 plus 4 plus I open brackets. I'll add the imaginary parts together separately. 3 plus negative 1, where the negative 1 is the coefficient of the complex operator. And at this point, I'm going to get 2 plus 4, 6, plus 3 plus negative 1, 2i. So simply, Z1 plus Z2 is 6 plus 2i. And that is how we go by addition of complex numbers. Using the same values for Z1, Z2, let's find Z1 minus Z2. This will be equal to 2 plus 3i minus 4 minus I, right? I'm going to get 2 plus 3i minus, so at this point, I can refer from the general formula I quoted. So the basic thing to do here is to take the row parts, the 2 and the 4, then we subtract them separately in one bracket, plus I, then I take 3 here, minus the coefficient of what? My operator, also separately in one bracket. 2 minus 4 is equal to negative 2, plus I open brackets, 3 minus minus 1, which is 4, and this is equal to negative 2 plus 4i. And this is how we go about the subtraction. Anyways, somebody will prefer to also expand this bracket because addition and subtraction are almost the same, just the sign that changes. So at this point, the person can straight away write 2 plus 3i minus 4, that is this, then minus minus will give us plus I. So 2 minus 4 is negative 2, 3 plus I is what? 4I. And this is the same as what we have here. So this is how we also go by subtraction of complex numbers. These are basic arithmetic involving complex numbers, and you should know on your fingertips. You either add or subtract the real parts separately, then you subtract or add the imaginary part separately, and you attach it to the I. As simple as that. Now, using the same values of z1 and z2, let's quickly find the product. So find z1 z2, that is z1 times z2. This is equal to 2 plus 3I multiplying 4 minus I, right? So this is simply going to give us the normal expansion. As you know, if you have A plus B multiplying another, let's say A1 plus B1 multiplying A2 plus B2, and a normal binomial expansion, this will take this will take this, then this will take this, and this will take that. It's the same thing we do here. So the first thing to do is you take the 2 here, open bracket, multiplying 4 minus I, right? Plus the 3I here, open bracket, multiplying 4 minus I. As simple as that. At this point, we call this decomposition. So we've decomposed this to give us this. Let's multiply through and see. 2 by 4 will give us 8. 2 by negative I is negative 2I. Plus 3I times 4 is plus 12I. Then 3I times negative I. So let me see, plus 3I, open bracket, 3I, negative I. Let's see how you do this. I'll have my 8 back again, but negative 2I plus 12I will give us plus 10I. Then I'll have I times negative I to give me what? Negative I squared, right? So if you have I multiplying I is equal to I squared, and there's negative already here, so it's going to give us negative I squared. We all know that negative I squared is equal to negative 1. So I'll have negative 1 and I'll get positive 1. So at this point, I'll get this, and this will give me positive 1. So I'll get 3, right? Once I get 3, I'll have 8 plus 3 to be 11 plus what? 10I. So the multiplication of complex numbers also follows the same procedure as we do in our normal binomial expansions. This is all for the arithmetic for now. Let's quickly move to the equality of complex numbers. But before we do the equality, okay, let's do the equality. So equality of complex numbers. When we are talking about equality of complex numbers, I may have a complex number z1 to be equal to z2, provided their row parts are equal. So the row parts of z1 should be equal to the row parts of z2. Then the imaginary parts of z1 should be equal to the imaginary parts of z2. 3 plus 2I, and z2 is equal to 2a plus bi, right? Find the values of a and b if z1 is equal to z2. So we have this problem here. We have z1 to be equal to 3 plus 2I, z2 to be equal to 2a plus bi. We have to find the values of a and b provided z1 is equal to z2. But take note, from the equality, it says the row part of the z1 should be equal to the row part of the z2. So I can say 3 here is equal to what? 2a here, right? Therefore, a is simply equal to, you divide here by 2, here by 2. And a is simply equal to 3 out of 2. Now we can have 2i here to be equal to bi. Therefore, the I will cancel I and we get B is equal to 2. So B is equal to 2. So this is a simple scenario of equality of complex numbers. Let's see another one. So if Z1 is equal to 3 minus I, Z2 is equal to A plus A minus B I. Find A and B if Z1 is equal to Z2. So we have been given Z1 to be equal to 3 minus I, Z2 to be equal to A plus A minus B or I. The question is, find A and B if Z1 is equal to Z2. The rule is the row part of Z1, so row part we say RE of Z1 is equal to RE of Z2. Then the imaginary part of Z1 is equal to the imaginary part of Z2. At this point, the row part of Z1 is simply 3. The row part of the Z2 is simply what? A, right? Therefore, A is obviously equal to 3. Imaginary part of Z1 here is the coefficient of the operator, which is -1. It is -1 because the general representation of complex numbers is A plus, not negative. So since the general representation is positive and here is negative, we can say that the coefficient of I is -1. In Z2, the coefficient of I is A minus B. And now we can find the value of B since we know the value of A. So -1 will be equal to 3 minus B. Then I'll bring B here, I'll bring -1 here. So B will simply be equal to 3 plus 1, which is equal to 4. So A equals 3, B equals 4 from equality of complex numbers. Let's quickly move to graphical representation of complex number. Graphical representation of complex numbers. So whenever you have a complex number, Z is equal to, let's say, X plus IY. You can compare this to the linear graph Y is equal to MX plus C, right? Where Y is the Z, X is X, X here represent the Y here, our M represent the I operator, then C represents what? X. Is that not it? So let me write it here. Z is equal to IY plus X. So you can see that this has some kind of correlation with this. For that reason, generally, complex numbers can be represented on a plane, which we call the complex plane, but it has a name called the Argand diagram. On the y-axis, we have what we call the imaginary, that is I. On the x-axis, we have the row parts of the complex numbers. This is the negative imaginary, and this is the what? Negative row parts. Is that not it? So every complex number can be represented graphically on the Argand diagram. Let's see how we represent complex numbers on the Argand diagram. So I have a problem here. Represent the following complex numbers on the Argand diagram. So this problem, I have the A part to be equal to -3I plus 2. I have the B part to be equal to 4 plus I. C, let's say 2I. Then D, let's say I have 1. Let's say 1. Yes, 1. To represent this on the complex plane, we simply get A. I'll draw my Argand diagram. This place is our imaginary. On the imaginary side, I will represent what? My imaginary part of the complex number, and on the real part, I'll represent the real part of the complex number here. So I'll just simply write 2 here. Then since here is negative, you know that on the Cartesian plane, negative imaginary will fall down here. So I have my negative 3 somewhere here. So this will come down to meet this, and you draw your complex number here as what? A, which is negative 3i plus what? 2. So this is how we do it. So this is the meeting point, and you draw it from the origin O. So our complex number A has been represented as this form, as A. And let's see the B. 4 plus I. I'll simply make a sketch. Since 4 is on the row part, it will take somewhere here. Then this part here is the imaginary, and it's 1. Because this is already I, imaginary I. And they will meet somewhere here. So this is our B, and it's given by 4 plus I. So I'll join here like this. Then here is the origin. Likewise C. So C will be represented as, I'll have my complex plane this way, and it's 2i. The real part is 0, meaning that I'm going to represent it on the imaginary part, which is 2i. So I'll just tap 2 here because this part has the imaginary entries. So from the origin 0, it will just fall here. So that's how we see purely imaginary numbers. So take note, a complex numbers which has only imaginary parts present is purely, so you say pure imaginary complex numbers. Then you have a pure real complex number. That means that for this pure imaginary, it has no real parts, and the pure real has no imaginary parts. Now let's represent the last one, D, which is 1. So you still have your I being the imaginary axis, and here's our real axis. So represent the 1 somewhere here, 1. So it's simply this way, the origin to the 1. So we simply mark the side, and this is the representation of 1 on the Argand diagram. Moving from this part, we simply go to modulus and argument of complex numbers. Modulus and argument of complex numbers. This is an important part of complex numbers, and it usually appears in exams, most exams, that is algebra exams. So please pay the maximum attention at this part. Starting with the modulus, let me refer you from the Argand diagram. If I draw something like this, from the origin, I locate a complex numbers here. Where here is, let's say, 1, this place is, let's say, 3. This is my imaginary axis, this is my real axis, RE. My complex number is represented as a linear, a line, which is connecting the 3 on the imaginary axis to the 1. The distance from the origin O to the complex number Z is what we call the modulus distance. So the modulus is simply equal to the distance OZ, right? Origin towards Z. Now, to find distance, basically distance is given by the general formula. If I have a point xy in a plane, and if I want to measure a distance from the origin 0, 0, this is simply equal to the square root of the expression x minus 0 all squared plus y minus 0 all squared. We apply the same principle here. So the rule is, for every general complex number representation as z is equal to x plus iy, the modulus is simply equal to the square root of x squared, that is the real part, plus y squared, that is the imaginary part. So this is how we find the modulus of complex numbers. Let's take an example here. I have a complex number, so find the modulus of the following complex numbers. So I have my A part, I have, let's say, 2 plus 3i, B, let's say 4 minus 2i, C, let's say 3i. Now let's take the A, 2 plus 3i. I want to find the modulus of what? Z. Now modulus of Z, we just simply put it in 2 bars. So these 2 bars, when you see it around a complex number, means that we are finding the modulus of that particular complex number. So this is simply equal to the square root of my raw part, which is 2 squared, plus the imaginary part 3 squared. And finally, I'll get square root of 2 squared 4 plus 3 squared, which is what? 9, giving me square root of 13. For my B part, I'll have absolute of Z, which is the distance or the modulus of Z, to be equal to 4 squared plus negative 2 all squared. That is for this part. Hence, you know that 4 squared is 16, then negative 2 squared is what? 4. I'll simply get square root of 20 as my modulus. Now, for the C part, I have 3i, so the length of Z or modulus of Z is simply equal to, the raw part is 0, right? This is the same as plus 0, so 0 squared plus 3 all squared. And this is going to give me square root of what? 0 plus 9, which is equal to square root of 9, and the answer is 3. So this is simply how to find the modulus of complex numbers. Let's quickly go into the argument of complex numbers. Argument is just a basic English word which is not to argue in this manner. It's a technical term in complex numbers which we want to find the angle of the complex number from the positive x-axis. I'm going to use the Argand diagram to explain vividly the argument of complex numbers. On the Argand diagram, as I have said earlier, has the imaginary axis as the y part, and it has the real axis to be the what? X part. If I represent any arbitrary complex number as z having x plus iy, z will have a distance from the origin O as what we call the modulus of z, right? You realize that this c is making an angle with the positive x-axis, theta. So in the Argand diagram, a complex number is fully defined by its distance from the origin as well as its angle it is making with for the positive x-axis. So meaning that this complex number z has this length from here to here, as well as it has been moved away from the x-axis by the angle theta. So the representation of complex number in the Argand diagram gives it 4 characteristics, which is the modulus as well as the what? Argument. How do you find the arguments in that case? So let's see, let's apply some trigonometry here. When I complete this, it forms a triangle, right? I'll have my x part and I'll have my y part. And you know about SOHCAHTOA, right? So from the SOHCAHTOA, I realize that if you have this hypotenuse, this is the opposite and this is the adjacent. So adjacent, hypotenuse, and this is the opposite. If you want to find this angle theta, you know that tan theta is simply equal to y on x, right? And generally, we know that y is the coefficient of the imaginary part of a complex number. Z is equal to x plus iy. And x is the real part, meaning that the argument represented as arg of a complex number z is simply equal to tan inverse of y on x. That is tan inverse of its imaginary coefficient over what? The real part, like this. It doesn't end here. Now let's see how we can find the argument in all cases. So whenever you are dealing with arguments of complex numbers, we have 2 main conventions, and I will be showing you very soon. But before that, let's solve some few examples so you know how to find the arguments. So let me give an example here. So find the argument of the following complex numbers. So I'll have my A, which is 1 plus I. Then I'll have B, which is simply equal to 2 minus I, right? So let me make it negative 2 plus I instead. I'll explain why. So let's find the solution for this problem. If you are not asked find the arguments, they will simply say find arg of the complex numbers. For modulus, they'll just simply put the z into bars. Take note of that. So considering the first one, 1 plus I, argument of 1 plus I, as I said, is equal to tan inverse of our y on x, where y is the coefficient of what? Our imaginary part. In this case, I have tan inverse of 1 on 1, right? You simply put this into your calculator and you realize tan inverse of 1 is equal to 45 degrees. In complex numbers, for easier computations, we normally represent it in pi radians instead of the degrees. So converting this to pi radians, we simply divide 45 over 180. And what is 45 into 180? 45 will go into itself 1 and go here 4. So you simply multiply pi by 8. So this is equal to 1 out of 4 pi. So the answer is either 45 degrees or 1 out of 4 pi radians. And that simply gives the argument of this. Let's see the argument of the second one. Negative 2 plus I. So to find arg of this, negative 2 plus I, as usual, tan inverse. Coefficient of the imaginary part is 1, the real part is negative 2. So tan inverse of what? Negative half, right? We simply punch this into your calculator and we are getting negative 26.56, right? So this is where the problem starts. So let's see. Whenever you are being given a complex number to find the argument, this is the negative angle we got. I'll have, so if you are given any complex numbers, any complex number to find the argument, it's advisable to represent it on the Argand diagram first so that you can effectively find its imaginary part. So this is the imaginary and this is the real axis. The complex numbers I got, the second one here is 2 plus I, right? Negative 2 plus I. So I'll have here, which is my negative row, and this negative imaginary. So my negative will fall somewhere here, then my 1 will come here. So my complex number will be on the second quadrant. So first quadrant, second, third, then fourth. I'll explain it very soon. So when the 2 is here, you realize that it's the angle theta is making with what? This axis. And that is what we call negative 26.56. But from the definition of arguments, the argument says argument theta is the angle a complex number makes with the positive x-axis. Take note, positive x-axis, not any other axis, but rather positive x-axis. Meaning that you are going to take the argument from this side until it touches the complex number here. So if here is negative 26.56, what will this whole bigger angle be? From angles in our high school, we know that supplementary angles or angles on a straight line sum up to 180. So negative 26.56 plus the theta which we are interested is simply equal to 180. So the raw argument is 180.44. When we divide this by 180, we are simply going to get 0.85 pi radians. So this is how we find the argument when the complex number falls in the second quadrant. Let me show you some special case. When I have this complex number on the Argand diagram, or any complex number on the Argand diagram, let's say this is my imaginary, this is my real part. I have my complex number z. Take note, our argument is saying that we take the angle from the positive x-axis, right? And you know that this is the positive x-axis. We can take it clockwise or what? Anti-clockwise. We have two ways. The first convention I'm talking about is the convention where theta is between negative pi and positive pi. So whenever you are dealing with arguments, the first convention, if you are applying to that, you make sure that your theta is always lying between negative pi and pi. This is what we call the principal argument. Then the second convention is theta will be greater than or equal to equal to 0, then less than or equal to 2 pi. So these are the two conventions, and I bet you any convention you choose, you arrive at the same answer. The angles may be different, but your complex number doesn't change. So let's see how this convention applies. Let me give an example here. Find the argument of the complex number z, which is equal to negative 4 minus 5i. So let's look at this interesting problem. I'm having on my complex plane negative 4 at this side and negative 5 at this side. So I'll have my complex, and always the angle is attached to the x or the real part, right? So at this point, this place becomes what? Tan inverse. That is theta. This theta here becomes what? Tan inverse of what? Negative 5 over negative 4. Also equal to tan inverse of 5 out of 4, right? You simply punch this into the calculator. Tan inverse of 5 out of 4. Then once you get this, the answer is equal to 51.30, right? So once you get 51.30, we ask ourselves, is this the argument? No. Argument, the rule says we should measure it from the positive x-axis, positive. So we should measure the arguments from this side. Let me show it to you from this side up to the complex number itself. So you just have to draw an arc to touch our complex number. But you know that to measure something from the positive x-axis, you can either take the path I choose, which is the anti-clockwise, or what is technically called counterclockwise, or you can take the clockwise mean, which is either from this side to this side. These are the two conventions I'm talking about. So if you want to go by this, we have, meaning you are going by the convention that our theta should be greater than 0 but less than or equal to 2 pi. So in this case, you add what? This whole angle to this to get our total argument. So let's say by convention 1, I'll have my argument to be equal to 180 plus what? 51.30. And that is going to give me what? 180 plus 51.30. That will give me 231.3. Now the second convention, let me use. So the second convention is here. That's the second one. You realize that I'm going to take it from the positive x-axis, but in this case, clockwise. We are taking it this way. And you know that if I want to find the angle here, provided I have here, this whole here is giving us what? 180. I need to subtract it from 180. But see, the counterclockwise is always positive and this side is always negative. So in this case, for us to find the angle here is indeed theta minus 180, right? So this is going to give us 51.30 minus 180, and that's going to give us, this is going to give us negative 128.7. So at this point, let's check if these two angles are indeed equal. Our complex number was initially -4 minus 5i, right? And we are saying that the argument theta is equal to either this or this. Let's see if you get our complex number back if you are using the right or any of these two conventions. So let's quickly find our modulus. Our modulus, which is equal to square root of what? -4 all squared plus -5 all squared. Is that not it? This will simply give me what? 16. This will give me 25, giving me square root of 41. From the Argand diagram, if I know the modulus here as what? Let's say r, and I know theta. Using r cos theta plus r sin theta, I can get this linear form back again. So now let's check. Root of 41 cos the first convention, which is what? 231.3 will give me what? So you can follow as I punch it to the calculator. Root of 41 cos of what? 231.3. This will simply give us -4. Now, assuming I'm using the angle -128.7, which is the second convention, I'm going to have square root of 41 cosine of -128.7, right? So once I have this expression, let's point that into calculator. Square root of 41 cosine of -128.7, right? And this will give me -4 as well. And what does this imply? No matter the convention we take, we are still going to have the same solution. But some questions, assuming you are doing MCQs, the MCQ, they must require this angle. Some too may require this angle. So if you do it with this convention and it doesn't, you don't see your answer in it, you can try this convention and you'll find it. And this convention normally applies to the third quadrant. That is where there is a controversy, because it's either this or that, right? So this is all about the argument of complex numbers, and let's move on to the next part of what you're doing. So let's quickly find the conjugates of complex numbers. There is a short part. So conjugate of complex numbers. So having this conjugate of complex numbers, what does it say? If you have a complex number z equals x plus iy, the conjugate is represented as z bar. There is a bar on it, so the bar indicates that it's conjugate of z. Generally, is given as x minus iy. What does this mean? The conjugate of a complex number is simply the negative imaginary of the original. So if, for example, you have z to be equal to 2 plus 3i, the conjugate z bar is simply 2 minus 3i. If I have an expression, let's say z is equal to 2 plus xy or I, the conjugate, don't worry yourself, just change the sign of the imaginary and you are going to get 2 minus xyi, and this is simply the conjugates of complex numbers. From here, let's find division of complex numbers so you understand. We reserved it when we were starting or when we were dealing with the arithmetic. For that reason, if you have z1 over z2, which is a complex number, x1 plus y2, plus y1i over x2 plus y2i. How do we solve this? To solve this, we simply apply the conjugate which we just did. So the rule is x1 plus y1i all over x2 plus y2i. You multiply it by the conjugate of this, the denominator. So I'll multiply it by x2 minus y2i over x2 minus y2i, and this will help me divide any complex number I come by. Let's take an example so you see how we apply this. So in our example, we are going to have simplify the expression um 2 plus 3i over 1 plus I. How do I simplify this? This is a simple division. I can do this by applying my conjugate. So conjugate of 1 plus I is simply equal to 1 minus I. So I have 2 plus 3i all over 1 plus I. Then we multiply the conjugates on both the numerator and the denominator. So 1 minus I. And what do I get? This is also multiplication. For the top one, I'll have the expression 2 plus 3i multiplying 1 minus I all over 1 plus I, 1 minus I. I further simplify this. 2 times 1 is equal to what? 2. 2 by negative I is equal to negative 2i. 3 times 1, 3i times 1 is equal to what? Plus 3i. Then 3i times negative I, which you have done before. You know, I by I is negative 1, making it positive. So you get plus 3. All over 1 by 1 is 1. 1 by negative 1 is negative I. Positive I times 1 is positive I. Then I times negative I will give us what? Plus 1. Because I squared is negative 1 times the negative is giving us positive. Obviously, we can see that this will cancel this. Then I'm going to have 2 plus 3, which is 5, minus what? Negative 2i plus 3i. That will give me plus I. All over, this is gone. So 1 plus 1 is 2. So the answer is 5 out of 2 plus 1 over 2i. And this is the simple form for the division of what? The complex number 2 plus 3i over 1 plus I. Just make use of the conjugates and you simplify as I have done. Having solved this, let's quickly move to the next part. The next part, I have what we call the polar representation of complex number. Polar representation of complex numbers. So for polar representation of complex numbers, a complex number in its linear form is given as x plus iy. In the polar form, we deal with what? R, which is the modulus, angle theta, which is what? The argument. And I was proving it in our previous example that if you have a complex number where here is y, here is x, this is the imaginary and this is the real part. If the complex number is in space, like this z, it has an angle theta with our positive x-axis. Therefore, if we find the length of what? This complex number, we call it r. And theta is the angle which is away from the positive x-axis. So the characteristics of a complex number on the Argand diagram is simply r, theta. If you have r and you have theta, using cosine or the trig ratios, you can get r cos theta. R cos theta will give us what? The x component. Then r sin theta will give us what? The y component. R sin theta will give us the r component. So the polar representation is just representing complex number in terms of its modulus as well as its argument. So this is also giving us r cos theta plus I sin what? Theta. Is that not it? Yeah. Then the third representation, what we call the Euler's representation. And that one is giving us r e to the power I theta. So these are the three major forms of the polar representation of complex numbers. Either r angle theta, r cos theta plus I sin theta, or r multiplying e to the power I theta. Let's see how we can convert complex numbers to the polar form. There are a lot of application of the polar form, so please pay attention for this side. Now I have, let's say, 1 plus square root of 3i. Convert this to polar form. Now, the Euler's representation is also called the exponential form. So they will just tell you that convert this to the exponential form or polar form. Anyways, you are right. To convert any linear form of a complex number to the polar form, the first thing we need is our r, that is modulus. The second thing we need is what? Theta, which is the argument. With these two parameters, we are good to go to find our polar form. So what's the modulus? As we've stated already, let's say this is z. The modulus tends to become z is equal to the square root of 1 squared plus square root of 3 all squared. And this will give me square root of 1. This will cancel this plus what? 3, which is equal to square root of 4 is equal to 2. Is that not it? Now let's go to theta. It's simply tan inverse of what? My coefficient of I root 3 all over 1. So tan inverse of what? Square root of 3 will give me what? You simply punch into your calculator. So that's going to give us 60 degrees. So 60 degrees, which is in the pi radians, 60 on 180 pi. This will go here. 6 goes into itself 1, go here 3. Our answer is 1 out of 3 pi. That is for our r and our theta. So at this point, we are simply going to find. So the polar representation, as the question asks us, is simply r angle theta, right? So I'm going to have r, which is equal to 2 angle 1 out of 3 pi, which is also equal to 2 cos 1 out of 3 pi plus I open bracket 2 sine 1 out of 3 pi. 2 cos 1 out of 3 pi plus I 2 sine 1 out of 3 pi. I'm going to expand this so right now we only want to convert it to polar form. So leaving it this way is enough, but it's good to factorize 2 out, then you get cos 1 out of 3 pi plus I sine 1 out of 3 pi. So this is the polar representation of the complex number given. You need your r, you need your what? Theta. Simple like that. In the exponential form or the Euler's form, r e to the power I theta, we simply get what? Our r, which is 2, e to the power I, and the theta is now what? Pi on 3. That is 1 out of 3 pi. So you simply get 2 e to the power pi on 3i. And this is also the exponential representation. So if you have two complex numbers which are in the polar form, let's say z1 equals r1 angle theta 1, z2 equals r2 angle theta 2. If you want to multiply these two as z1 times z2, we simply get r1 r2 then angle theta 1 plus theta 2. This is the first identity of the polar representation which I want to show you. If you are multiplying two complex numbers which are in their polar form, we simply multiply the real parts, then we add the angles together. So we simply add the arguments, then you multiply the real parts. If you have z1 over z2, that is division. You have r1 over r2, then you subtract the angles, theta 1 minus theta 2, as simple as that. So this is how we go by with division and multiplication of complex numbers represented in the polar form. Now, let's talk about the Moivre's theorem. The Moivre's theorem. So, this will be the last part for the first complex number class 1. So, the Moivre's theorem, when you say the Moivre's theorem, this is a theorem used in complex numbers. The Moivre's theorem deals with polar representation, so the polar form. Take note. The Moivre's theorem deals with polar form. So the first condition is until your complex number is represented in the polar form, you can't apply the De Moivre's theorem. What is the De Moivre's theorem is, and what does it say? If I have a complex number represented as r open bracket cos theta plus I sine theta, which is the polar form, if this complex number is raised to the power n, then this will give me r to the power n, then cos this n will multiply the theta, n theta plus I sine n theta. So this is what the De Moivre's theorem is saying. It's a simple law. Any complex number raised to the power an exponent, you will simply give the exponent to the real part, then you multiply the power by the argument. In the exponential form, r e to the power I theta, if you want to have any power, let's say n, this is simply done as r to the power n, e to the power I n theta. And this is how we apply the De Moivre's theorem in the exponential form. How do we apply the De Moivre's theorem? Let's solve one example for you to understand De Moivre's theorem. So first, I have this example here. Solve the expression 1 plus I to the power 6. So you can imagine if you are to solve 1 plus I to the power 6, you are to use the binomial expansion, which is very tedious. De Moivre's theorem will set in to make calculation simpler, but the condition says convert your complex number to polar form. Take note. To convert this to polar form, as usual, you need your r, which is the modulus, and it's simply equal to square root of 1 squared plus 1 squared. This will give us square root of 2. Then our theta, which is the argument, will give us tan inverse of what? 1 out of 1, since we have 1, 1. That is giving us 45 degrees, which is equal to 45 over 180 pi. 45 will go into itself 1 and go here 4. So our argument is simply 1 out of 4 pi. At this point, let's convert this to polar form. I have my r, which is square root of 2, open bracket, cos my theta is pi on 4, plus I sine what? Pi on 4, right? And at this point, you close the bracket and bring your 6. So what I have in here has been converted towards this form. For that reason, I am going to apply the De Moivre's theorem. And applying the De Moivre's theorem, this is what I do. De Moivre's theorem is saying that this 6 will affect the square root of 2 as to the power 6. But expanding this, you only have to multiply the 6 by the argument. So I have cos pi on 4 times 6 plus I sine pi on 4 times what? 6, right? So I'll have square root of 2 to the power 6. Then 2 goes here 2 and goes here 3. That is 3 over 2 pi. So cos 3 out of 2 pi by I sine 3 out of 2 pi. So this whole thing now has been simplified to give us this thing using the De Moivre's theorem. And this is how the De Moivre's theorem works. As I said, De Moivre's theorem only works for polar form representations. Now, what's the usefulness of the De Moivre's theorem? That is the applications of De Moivre's theorem. So for applications of De Moivre's theorem, let's see some problems here. So the problem we are going to solve here, it says express sine 3 theta and cos 3 theta in terms of powers of cos theta and sine theta. So application 1, we are dealing with trig identities. So an application of the Moivre theorem is in trigonometry identities. So the problem here is express sine 3 theta and cos 3 theta in terms of powers of cos theta and sine theta. Watch closely as I solve this problem. So for the solution, I have sine 3 theta and cos 3 theta. So what I'm going to do now is, by the Moivre theorem, if you have cos theta plus sine theta, that is I sine theta, sorry, all to the power n, the answer is what? Cos n theta plus I sine what? N theta. Is that not it? From this side, I can say that cos theta plus I sine theta all to the power 3 will give me cos 3 theta plus I sine what? 3 theta. From this, I can easily solve the problem given. I will expand both sides and now compare it to the right side. Using binomial expansion, any number cube, you have 1, 3, 3, 1, right? That's the coefficient. I'll have my cos cube theta plus 3 cos squared theta, then I sine theta will follow. I sine theta. Then plus another 3, but this time this will reduce as cos theta, then I sine theta will now be squared. Then finally, I'll have 1 I sine theta all cube, right? This should give me cos 3 theta plus I sine 3 theta. At this point, let me simplify further. So I have cos cube theta, I have plus. Now, I'll have I3 cos squared theta sine theta. This place, I squared will be negative 1, right? So I have negative 3 cos theta sine squared theta. Check. Then this side will give me I cube is negative I, so minus I sine cube theta. Now, to find the corresponding expressions for cos 3 theta and sine 3 theta, I have to separate this into components of real parts and imaginary parts. For my real part, I'll have cos cube theta, then I'll have what? This side. So before we separate them, let's do some little expansion here. Cos cube theta, right? Then the other real part will be minus 3 cos theta sine squared theta plus I 3 cos squared theta sine theta, right? Then minus I sine cube theta. At this point, everything I have here is still equal to cos 3 theta plus I sine theta, right? So you can clearly see that I have separated this into real parts and what complex parts. But before I continue, I need to change the squared in it. So you know sine squared theta is equal to 1 minus cos squared theta from trig identity. So I'll simply have cos cube theta minus 3 cos theta. Then I'll replace this with that expression 1 minus cos squared theta, right? Plus I3. Then cos squared theta here, I'll also represent it with what? 1 minus sine squared theta. Is that not it? So 1 minus sine squared theta sine theta. Like this. Then minus I sine cube theta. So let's finish this. At this point, I'll have cos cube theta minus 3 cos theta minus 3 cos cube theta. Then at this point here to give me plus c 3i will be out. Then I'll have sine theta, then minus sine cube theta minus I sine cube theta. So let's still simplify. Now I'm having, so this one I'm having when you're multiplying, negative 3 cos theta will be here, then this should be plus. Check. So I'll have this plus this to give me 4 cos cube theta minus 3 cos theta, this side, right? Plus, I will factorize I out, but I have I3 here, so let me expand here. I'll have I3 sine theta, then minus I3 sine cube theta, minus I sine cube theta, right? So let me have this side I'm done, but for the I side, let me take I out. I'll have 3 sine theta minus 3 sine cube theta minus sine cube theta, right? So I out, this will stand there alone, 3 sine theta, but negative 3 sine cube theta minus sine cube theta will give us minus 4 sine cube theta. Then we can clearly see that we have decomposed them into only cosine and what? Sine, right? So see, this is equal to cos 3 theta plus I sine 3 theta. The problem was express cos 3 theta and sine 3 theta in the powers of cosine and sine. And we can clearly see that my raw part is equal to my raw part from equality of complex numbers. So cos 3 theta will give me what? 4 cos cube theta minus 3 cos theta. And my sine 3 theta here, which has the coefficient, which is the coefficient of I, will take this 3 sine theta minus 4 sine cube theta. We've expressed it in powers of what? Theta and what? Sine and cosine of thetas. This is a simple application of the Moivre's theorem. Then we have more applications to go. This being the first class, I would like to end the first part of the complex numbers, and we continue with the second part with the nth root of a complex number as well as with the complex logarithm, then other stuff. So thank you for being with me in this first class, and hope to see you in the next class for the second part of our full calculus.